We have been discussing the design of the finite impulse response filter, and we had explained what finite impulse response filter is and some of the characteristics of this filter. We saw that we have quite a number of methods that can be used to design the FIR filter, which included the Fourier transform method, Fourier transform method. We discussed the Fourier transform method of designing the filters. We have the window method, and our today's discussion will be based on the window method. Window method is actually an improvement of other methods of designing the filters, like the Fourier transform method. So we also want to see how the two are related. The other methods that are also there, as we discussed in our previous lesson, were the frequency sampling method, frequency sampling method. We discussed, we also stated the optimal filter design. So I will move ahead and with the discussion of the window method of designing the filters. So we had seen that we can use the Fourier transform method to obtain the desired filter coefficients. And we saw that in Fourier transform method, we start with the transfer characteristics of the filter that we want to obtain. Like we know that in the frequency domain, the transfer characteristic of the filter is in this form. So we start from this known filter characteristic, and then we design the filter coefficients. But there's usually a problem if we have a sharp change in the filter characteristics. Because what this means is that in the time domain, we are going to have several sidebands. We are going to have, if we just truncate in the time domain in this manner, then eventually when we obtain our time domain, function, then what we'll find out is that we would have several variations in this passband region, passband. You won't just have a constant like this. And even in the stop band, you would not just have a constant value. You would have some fluctuations in those bands in the stop band. And sometimes we call them ringing artifacts, ringing artifacts. So we won't just have a filter exactly where we don't have these variations in the passband and in the stop band. So to remove these ringing artifacts, then we can actually create a window so that the moment we have our signal, we pass it through a sort of window that is going to truncate the portions we don't want. so that they don't pass through the window. So that is where the window concept comes from, that we can pass our signal through a restriction, like a physical window, so that it is shaped, takes the shape of the window in some manner. So the so-called window functions have been defined, and we have several of them. We have several of window functions, so that eventually when we obtain our signal, um, our window, our filter coefficients, like let's say the h of n, then the windowed coefficients, we need to multiply h of n by the corresponding window function, the corresponding window function. So we have quite a number of window uh, functions that have been um, used to design the FIR filters. The simplest that we can have is simply called a rectangular window. So in a rectangular window, actually the window does not really cause any change in the filter characteristics. It is like creating some window just having an amplitude of 1, and then passing the signal through it. So that if the signal had some characteristics outside this window, then now those ones which are outside the window will not be passed, because the signal will take the shape of the window. So a rectangular window would be defined by W rec for rectangular equal to 1 for the whole range of the filter coefficients. Then the other window that we have is triangular or Bartlett window. Triangular. We also talk of Bartlett window. So the characteristics of a Bartlett window is given by W triangle n equal to 1 minus n over m for the all of the range of the filter coefficients. Then we can also talk about the Hanning window. We also have the Hanning window having the characteristic given by W Han n go to 0.5 plus 0.5 cos n pi over m for the all of the filter coefficients. We also have the Hamming window. Don't confuse the Hanning and the Hamming. Hamming window defined by W ham equal to, of course, W ham n equal to 0.4, to just write this in log, so that we have W ham for Hamming n equal to 0.5 plus 0.46 n pi over m for the whole of the filter coefficient range. We have also the black window given by W black and of course equal to 0.42 plus 0.5 cos n pi over m plus 0.08 cos 2n pi over m. We have other window functions which we have not listed here. Like another popular one is called Kaiser window. You can check the characteristics of the Kaiser window from the books. So what would be the design procedure of the filters using the window method? So using the window method, the first step would be to obtain the filter coefficients through the Fourier transform method. Obtain the filter coefficients through the Fourier transform method. We had seen how this one is done in our previous lesson. Then after that, multiply the generated FIR coefficients, the generated FIR coefficients by the selected window sequence, i.e. the selected window sequence, so that we have the resultant coefficients which have been windowed being given by h of n, which are the coefficients of the filter which have been designed using the Fourier transform method multiplied by the window coefficient, corresponding window coefficient for n from minus m all the way to 0 to 1 up to minus m. We'll see this with the help of an example where wn is one of the window functions, is one of the window functions, is one of the window functions. And finally, as we had seen, we need to come up with a causal filter. So we may need to delay the determinant coefficients so that we obtain the filter coefficient, the resultant filter coefficients. You can refer to the previous slide for a detailed discussion of this. So the third one, delay the windowed impulse sequence H, W, or N by M samples to get the required in FIR coefficients by M samples to get the required windowed FIR coefficients. Of course, we use the same formula that we had used previously. That is B of n equal to HWN minus 1, or n equal to 0, 1 up to n. So we'll go through an example to see how we can design a filter based on the window method. So let's have an example. This is the same example we had done in the previous slide on how we can use the Fourier method to design a filter. So A, design a three-tap FIR low-pass filter with a cutoff frequency of 800 hertz and a sampling rate of 8,000 hertz using the Hamming window function. Using the Hamming window function. Then part B, determine the transfer function and the difference equation of the designed FIR system. Determine the transfer function and difference equation of the designed FIR system. So let's see how we can go through this problem. But we are going to use the results that we had obtained from the previous experiment. So, sorry, from the previous slide, because we saw that first of all, if you look at the procedure that we need to use, then we need to obtain the FIR coefficients through the Fourier transform method. Obtain the FIR coefficients through the Fourier transform method. So we'll just bring the results that we had in our previous example so that we can use them here. Instead of redoing um, everything, we had found out that in that previous example, that H naught was equal to 0.2 and H minus 1 was equal to H1, which is equal to 0.1871. So how do we now apply the Hamming window function? Apply the Hamming window function. Check and see what the Hamming window is. Of course, these functions, we should be able to refer to them. We may not have them in our heads because we have the functions that are listed here, but we may also have some other functions which have come into being, which can also be used to design the filters. So you can see there for the Hamming window, the Hamming window is here. We have the Hamming window given here. 0.5 plus 0.46 n pi over m. So we need to write it down there. That we have our Hamming window being given by W Ham n equal to 0.5 plus 0.46 n pi over m. Remember, because we are still moving on with the previous example, we had 2m plus 1 equal to 3. So that m is equal to 1. So if we apply this to the Hamming window, then we would get W Ham 0 when n equal to 0 here. Put 0 everywhere. Put n equal to 0 there. You can see if you put n equal to 0, the whole of this term would be equal to 0. Oh, there's a problem. There's a problem with the way I wrote the function. We actually have this function should actually be this. Should actually be can confirm this from other sources. 0.46 cos n pi over m. This is the Hamming window. I can go up and do the change. I can go up and do the change Hamming window. No, it's actually, yeah. The others are okay. We left the cos here. So we can use it down here. So we have 0.5 plus 0.46. Now, let me see the Hamming window. What is it in the Hamming window? Are we right? Hamming window is 0.54. No. Oh, by the way, how many windows should be 0.54. Should be 0.54. No, it's fine actually. 0.54. Yeah, it should be 0.54. 0.54 plus it's plus 0.46 into cos 0, n is 0, pi over 1. Cos 0 is 1, so this gives us 1. So that gives us WHAM 0. Then WHAM 1 would be 0.54 plus 0.46 cos 1 times pi over 1, which would actually give us 0.08. 0.08. Of course, we'll also have W harm 1 equal to W harm minus 1. So we need now to apply the window functions by multiplying the corresponding coefficients in the window function to the corresponding coefficients in the Fourier transform method. Like in the Fourier transform method, we had found H0 to be 0.2. So we basically have the filter coefficients HW0 would be equal to H0 for the Fourier transform method, because it is what we are windowing. So we multiply it by the corresponding window function, W harm 0 also. So this one we have found to be 0.2 multiplied by 1, because W harm is equal to 1. So you get 0.2. Then we also go to HW1 equal to H1 times W harm 1, which H1 we are determined up here to be equal to 0.187, 0.1871. So we have 0.1871 multiplied by W harm 1 is, we have found it to be 0.08. 0.08. So this one gives us 0.1497. Then W minus 1 is also equal to H minus 1, W harm minus 1, which is equal to 0.1871 times 0.08, which also gives us 0.1497. Therefore, if we delay the HWN the way we had done in the previous slide where we were designing our filter using the Fourier transform method, then we'll have that is delaying HWN by M equal to 1 sample gives B naught equal to B2 equal to 0.01496 and B1 equal to 0.2. So that gives us all the coefficients or the windowed function. So you have seen that the moment we have obtained our filter coefficients using the Fourier transform method, then the corresponding coefficients by using the window function, we multiply the corresponding values. And that is what this formula shows. Multiply h of 0 by wh of by wn, depending on the chosen window function. Then the rest of the solution of this problem would proceed as in the previous example, because what we simply need to do is to write down the transfer function. That is, we'll have the transfer function being given by h of z being equal to 0.01497 plus 0.2 z minus 1 plus 0.01497 z minus 1. Therefore, y of z, x of z equal to, oh, sorry, this is z minus 2, equal to 0.01497 plus 0.2 z minus 1 plus 0.01497 z minus 2. And if we proceed the way we proceeded with the Fourier transform method and get the required transfer function in the time domain, then we would have y of n equal to 0.01497 x of n plus 0.2 z minus 1 x of z plus 0.01497 z minus 2 x z. Oh, sorry, I've mixed this with the z's. Maybe I would have this one in terms of z first, and this one also in terms of y of z, so that I can now have my y of n by getting the inverse transform of this equation, so that I have 0.01497 x of n plus 0.2 x n, that's 1, plus 0.01497 0.01497 xz. And this will be the filter response in the time domain. So that would mark the discussion on this slide. I will provide some examples for you to, some examples for practice for you to be able to work them out, and so that you appreciate more how the design is supposed to be done.